Now let's look at the sign of the potential. The electric potential is defined as the potential energy per unit charge. You notice that we've taken the work when moving from R to infinity, whereas for gravitational potential energy it goes the other way. Why? It's just a question of what limits you've chosen. The potential is always a difference between 2 points, even if one of them is infinity, just as potential energy is a difference between 2 points. If we take the limits the other way round, which is going from infinity to R to match gravitational potential energy, we just put a minus sign in front. We don't worry about negative energy anymore, because the change in energy is all that matters, and the sign just tells you whether energy has been lost or gained. So the thing to remember is that a positive particle Q has a positive potential V around it, and a negative particle Q gives a negative potential. To illustrate, let's have a look at some graphs of potential. The top left shows gravitational potential for comparison. You notice that it slopes down towards the planet because that's the direction of the force on the test mass. At top right, you see the potential near a positive charge. It slopes down away from the plus Q because that's the direction of the force. At bottom left, the potential around a negative charge is like a gravitational potential. The electric field would make the test particle, which is positive, move towards the negative charge. So that direction means lower potential. For your interest, we've shown the potential in an atom at the bottom right, because that has a central positive charge but an orbiting negative charge. So the force is attractive, and it would take work to pull the electron away. Some important points about potential. It's just a proxy for potential energy. It lets you compare what the potential energy would be at 2 places while keeping it independent of the particle. So it depends on spatial quantities only. Potential is a scalar quantity. It has a magnitude everywhere, but not a direction. This makes it much easier to use than electric field. The potential has units. The SI unit for potential is the volt, and 1 volt equals 1 joule per coulomb, because potential is potential energy divided by charge. The electric field and the electric potential are very intimately tied together. If we know what the field is, we can work out the potential, and vice versa. Let's have a look at an example. We're going to find what would be the potential at a point half a metre away from a charge of 1 coulomb. So let's put our charge here. We have Q, and this time we know that Q is 1 coulomb. And then half a metre away, so let's call that R is 0.5 metres, we will have this point P. And we want to know the potential at P. So it's actually a function of R, really, because the only thing that decides that potential is the distance away from the point charge. So we know that the R is Q over 4 pi E naught R. So Q here is 1 coulomb. 4 times pi times 8.854 by 10 to the minus 12 times 0.5. And that gives us a rather large number here, 1.8 by 10 to the 10 volts, which I could write as 18 gigavolts, which just gives you an idea, again, of how very large 1 coulomb is.